Hello, my name is William WEHRBAR, and this is my data science project on assessing the U.S. student loan market. The problem to be addressed during this project is the inefficiencies in the student loan market. Many economists are predicting that the student loan market is the next bubble to pop, similar to the housing market collapse during the financial crisis, albeit on a smaller scale. If we can accurately predict a school student body overall loan default rate, then that model could be used both for creditors and student borrowers as a means to calculate optimal student loan terms. The dataset to be used for this project can be found on the U.S. Department of Education's website. The dataset contains more than 4,800 schools from 2013 to 2015. Some of the variables included are the length of the longest program offered by the institution, the school type, number of borrowers in default, as well as several other variables. I'll be looking at the 2015 dataset as that is the most recent set of data we have available. I want to build a couple of different machine learning models targeting a school's overall default loan rate to see if we can predict that variable based upon feature variables in the data. On this slide, we have a detailed breakdown of the variables in the dataset. Other than the official cohort default rate variable, which is the variable that I'm going to try and predict in the models, the program length and the school type variables in particular are two variables that I'm also interested in, and we can see the categorical breakdown of those two variables on this page. Let's now take a look at the distribution of the program length variable, which is the length of the longest program offered by the institution, and the distribution of the loan default rate for 2015. As we can see here, neither variables are normally distributed. We can also see that for the loan default rate variable, distribution is clearly skewed to the left. For this plot, it is important to remember to use the as numeric feature when running the histogram function in R in order to get this plot to show. On this slide, we can see the relationship between the default rate and the program length variable, as well as the default rate and the school type variable. For the plot on the left, we can see that lengths equaling 3, which is non-degree one-year academic programs, look to have the highest default rate. On the other end of the spectrum, program length equaling 1, which indicates schools offering graduate or professional degrees, appear to have relatively low default rates. My interpretation of the school default rate and program length plot is that there's a relationship between how much a student invests in their academic career path and the default rate. For non-degree one-year academic programs, we see higher default rates, perhaps indicating that with relatively little time invested in these programs, students are not as concerned with the negative consequences of defaulting on student loans that are only accumulating over 1 year, and perhaps the opposite is true for schools offering graduate and professional degrees. For these groups, perhaps since students are more invested in a longer academic journey, they have stronger incentives to not default on student loans that would be accumulating over several years, which obviously means a much higher principal loan balance that would need to be paid off. That being said, I don't want to overinterpret this plot, however, specifically since I don't know if this is a causation or correlation. Does the amount of time invested dictate whether or not a student will default on loans? Or is it more so that students who pursue a graduate degree, for those students, they're inherently more likely to avoid defaulting on loans even before college? Now let's look at the plot on the right. The default rate in the school type plot is pretty easy to interpret. For school type equaling 3, which is proprietary, for-profit institutions, they clearly have higher default rates compared to other schools. I now want to create a data frame containing 2015 data for the variables that I am interested in for an R-part decision tree, as well as a random forest machine learning model. I'll be looking to predict a school's overall student body loan default rate using the different feature variables shown here. After splitting 70% of the data into a training set and leaving 30% as a testing set, in case anyone would like to compare a model to the test set, here's the first R-part model that I have built for this project. I'm trying to predict the default rate based upon all the different feature variables listed in the formula on this slide. The first split improves the model fit the most based upon how much relative error has decreased. We see 0.2219 in that first CP column, as n split goes from 0 to 1. The last split adds a little value in decreasing relative error. A tree with 11 splits minimizes the relative error for the Tree 15 model. I could look to apply the one standard error rule, which says that we should choose the model whose error is no more than one standard error above the error of the best model. People use this rule for the purposes of efficiency, and they're looking at marginal computational time compared to marginal decrease in error. I, however, do not think that that rule is necessary for this model, since the data set that I'm working with isn't too large, so computational constraints is not a big issue for this exercise. We still have a pretty high error rate for this model, so now I want to take a look at a random forest model to see how that performs as well. For the random forest model, I'm again going to try and predict a school's overall default rate based upon the same feature variables that I used in the R-part decision tree model. Taking a look at the variable importance plot, it makes sense that the x dot numerator and x dot denominator were high on the list, since those variables are used to calculate a school's default rate, where the default rate equals the number of students in default, x dot num1, divided by the total number of students, x dot denom1. It also makes sense that the program length variable ranks high in variable importance based upon my data visualization plots that I created earlier. But I am a little bit surprised to see zip code ranking higher than school type on the plot on the right-hand side. Perhaps my model is not fully capturing the importance of schools with a school type equaling 3, meaning for-profit schools or proprietary schools. My next step is to conduct some feature engineering, where I deconstruct the categorical variable school type. I know based upon the exploratory data analysis that there appears to be a significant relationship between school type and a cohort's default rate, specifically when it comes to proprietary institutions. To better exploit the differences in school types, I want to transform the school type variable into a binary feature where proprietary institutions have a school type value of 1 and all other institutions have a school type value equaling 0. I will create a duplicate copy of the data frame used in my Tree 15 model, previously used in the other models to do so. Compared to the original decision tree 15, the newly created decision tree, tree ST15, with my newly created binary school type variable, it has a lower root node error and lower X standard error for each corresponding CP. The plot CP function gives us the relative cross-validation error for different tree sizes, and it appears that n equaling 11 minimizes the relative error with respect to the geometric mean. One could perhaps interpret this visual as n equaling 12 minimizing the relative error, but that would add additional computation in exchange for little marginal improvement in terms of minimizing the relative error. I now want to build a prediction table and a confusion matrix for the newly created models to assess how well the models performed in terms of predicting a school's overall default rate. The U.S. Department of Education makes decisions on allocating Pell Grant funds using hold numbers. A 30% default rate is the cutoff for Pell Grant eligibility, so I want to round whole numbers before building. Once I have the confusion matrix built, I can now determine the accuracy by dividing the sum of the diagonal of the confusion matrix, CM, which is the correct predictions divided by the total sum of the confusion matrix. As we can see here on this slide, unfortunately the R-part model's predictions were not very accurate at all, around 5%. Let's now take a look at a random forest model with this newly created binary school type variable. Once I have built the confusion matrix, I can run the same calculation to determine the accuracy of the random forest model. The random forest model accuracy was significantly better than the R-part model accuracy at around 23%, however, still underwhelming. Even though the accuracy of the different machine learning models wasn't very good, this still was a worthwhile exercise for a couple of different reasons. Based upon the models, we could see that program length, the length of the longest program offered by the institution, and school type, specifically if a school is proprietary or not, are relatively important features in the data with respect to trying to predict the default rate. Students who are more committed to their academic career in terms of finances and time invested are more likely to have lower default rates compared to their peers. This exercise brings up an important consideration when it comes to the privacy of personal data. I did not attempt to scrape any student loan data in addition to the data made available from the U.S. Department of Education out of respect for data privacy. If more data on student loan borrowers was collected with additional unique feature variables, I'm very confident that one could build a model with much better predictive accuracy. This is a very important trade-off to consider, and trust is a key factor. Would the collective body of U.S. student loan borrowers be willing to offer additional personal data to be analyzed in exchange for student loans that are more fairly priced? I assume the answer would be yes, but only if one could guarantee that data is kept private and not leaked or exploited for other uses. Of course, that guarantee is near impossible to make based upon a historical precedent of high-profile data breaches and also exploitative practices conducted by high-ranking executives across the country. This project also was an important lesson in understanding that a machine learning model is only as good as the quality of the data. Sometimes there isn't much of a recognizable pattern or predictive relationship between different variables within a data set. In situations like this, it is important for a data scientist not to attempt to overfit or extrapolate too much from a model that simply doesn't have much predictive value. This concludes my presentation. I'd like to thank you for your time.